For this problem, we are going to use the fact that energy equals Planck's constant times the speed of light divided by the wavelength. This is going to be the energy of a photon. And so H times C equals 1,242 electron volt nanometers divided by our wavelength. And blue light has a wavelength of 500 nanometers. So nanometers are going to cancel. And when I do that calculation, I get 2.48 electron volts. For the energy of red light, which has a wavelength of 633 nanometers, we're going to have 1,242 electron volt nanometers divided by 633 nanometers. Nanometers are going to cancel once again, and I get a value of 1.96 electron volts. Problem number 2, a blue photon of light does not produce the photoelectric effect when shined on a certain metal. Violet light does. We need to remember our Roy G. Biv. Where red has a wavelength of 700 nanometers, blue is 500 nanometers, and violet is 400 nanometers. So if violet at 400 nanometers is emitting a photoelectric effect, and blue at 500 nanometers is not emitting the photoelectric effect, that means that only wavelengths down from violet are emitting. So anything to the left, 500, 600, 700, 800, are not emitting, not producing the photoelectric effect. And so we can say that yellow, which is from to the left of the 500 nanometers of blue, and red are not going to, and also green, are not going to produce the photoelectric effect. Right? Indigo, we wouldn't necessarily be certain about because it's between violet at 400 nanometers and blue at 500 nanometers. Problem number 3, we have a certain color of light produces photoelectrons with a speed of 3.45 times 10 to the 5th meters per second when shined on metal, with a work function of 3.14 electric volts. Calculate the wavelength of this light. So we're going to use Einstein's work with the photoelectric effect. So we have, for his equation, Planck's constant times the speed of light over the wavelength equals phi plus 1/2 mv squared. And we're going to recognize that we need to find the wavelengths. We're looking for lambda. Well, from before we know that Hc was 1,242 electron volts nanometers over our wavelength, which is going to be in nanometers, equals our work function, which is our phi, 3.14 electron volts, plus 1/2 times the mass, and I'm going to run out of room here. So this is the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms. And I'm going to squeeze this in here, which is a horrible way to do this, times our velocity, which is 3.45 times 10 to the 5th meters per second. And I need to square that, because that's 1/2 mv squared. When I do the calculation for 1/2 times 9.11 times 10 to the negative 31st kilograms times 3.45 times 10 to the 5th meters per second squared, I get a value of 5 3.42 times 10 to the negative 20th joules. At this point, I want to note that I have a value of 3.14 electron volts, and on the left-hand side of the equation, I have 1,242 electron volt nanometers over my wavelength. So the only unit that I'm not happy with is my joules. We want to recall that 1 electron volt, or hopefully we are recalling, is equal to 1.60 times 10 to the negative 19 joules. So we're going to use that as our conversion factor for 5.42 times 10 to the negative 20 joules. So on the bottom we have 1.60 times 10 to the negative 19 joules, and that will convert to our 1 electron volt. Joules cancel, and when I did this on my calculator, I got 0.339 electron volts. Putting that back into our equation, we have 1,242 electron volt nanometers over our lambda equals 3.14 electron volts for our work, plus 0.339 electron volts from our kinetic energy. Combining those on the right-hand side, I get 1,242 EV equals 3.479. Solving for lambda, lambda then equals 1,242 electron volt nanometers over 3.479 electron volts, which cancel, giving me a value of 357 nanometers, which is equivalent to UV light.